The Mpemba effect seems paradoxical. We intuitively understand that it takes time for a substance to cool down or heat up. The hotter something is, the longer it should take to reach a lower temperature. So how can hot water, already further away from its freezing point, reach it faster than cold water? The answer, it turns out, is far from simple. Water is an exceptionally complex substance, full of quirks and anomalies. Its behavior, particularly when it comes to temperature changes, is influenced by a delicate interplay of various factors. While scientists haven't pinpointed a single definitive explanation for the Mpemba effect, several compelling hypotheses have emerged. These hypotheses explore a range of possibilities, from the effects of evaporation and convection currents to the intricate behavior of water molecules themselves. One of the earliest and most intuitive explanations for the Mpemba effect involves evaporation. This phenomenon, where hot water freezes faster than cold water, has puzzled scientists and laypeople alike for decades. The idea that evaporation could be a key player in this mystery is both fascinating and logical. We know that when water evaporates, it takes away some heat energy with it. This process is a fundamental principle of thermodynamics and is something we observe in our daily lives. This is why sweating cools us down. When our bodies heat up, we sweat, and as the sweat evaporates, it removes excess heat, helping to regulate our body temperature. Now imagine two containers of water, one hot and one cold. This simple setup can help us understand the dynamics at play. The hotter water will lose heat through evaporation at a faster rate than the colder water. This is because the molecules in hot water have more energy and are more likely to escape into the air as vapor. This means that the overall mass of the hot water will decrease more quickly. As the water evaporates, it leaves behind less liquid to freeze. With less water to cool down, the remaining hot water might reach its freezing point faster, even though it started at a higher temperature. This counterintuitive result is one of the reasons the Mpemba effect is so intriguing. However, while evaporation plays a role, it doesn't fully explain all instances of the Mpemba effect. There are other variables and conditions that need to be considered. Some experiments have shown the effect even in closed containers, where evaporation is minimized. This challenges the evaporation hypothesis and suggests that the phenomenon is more complex than it initially appears. This suggests that other factors must also be at play. These could include the properties of the water itself, such as dissolved gases, the behavior of water molecules at different temperatures, and the way heat is transferred within the water. Scientists continue to study the Mpemba effect, using advanced techniques and technologies to uncover the underlying mechanisms. Each new discovery brings us closer to understanding this enigmatic phenomenon, but also raises new questions and possibilities. The case of the disappearing water is a reminder of the complexity and wonder of the natural world, and the ongoing quest for knowledge that drives scientific inquiry. Another intriguing hypothesis centers around convection currents, the circular movements of fluids driven by temperature differences. These currents are a fundamental aspect of fluid dynamics and play a crucial role in various natural and artificial processes. Understanding them can provide insights into a wide range of phenomena, from weather patterns to industrial applications. When you heat a pot of water on the stove, the water at the bottom heats up faster than the water at the top. This is because the heat source is directly beneath the pot, causing the water molecules at the bottom to gain energy more quickly. As these molecules become more energetic, they move faster and spread out, decreasing in density. This hotter, less dense water rises, while the cooler, denser water sinks, creating a continuous circulation pattern. This process is not just limited to water. It occurs in the atmosphere, oceans, and even within the Earth's mantle. The rising and sinking of fluid masses due to temperature differences is a driving force behind many natural phenomena. These convection currents can influence how quickly a body of water cools down. In a natural setting, such as a lake or ocean, convection currents can distribute heat throughout the body of water, affecting the overall temperature and cooling rate. This is why understanding convection is essential for fields like meteorology and oceanography. In a container of hot water, these currents are more vigorous, leading to faster heat transfer and potentially quicker cooling. The intensity of these currents depends on several factors, including the temperature difference between the water and its surroundings, the size and shape of the container, and the properties of the fluid itself. The rapid movement of water molecules within the container might facilitate quicker heat loss, allowing the hot water to reach its freezing point before the colder, more stagnant water. This phenomenon, known as the Mpemba effect, has puzzled scientists for decades. It challenges our conventional understanding of thermodynamics and heat transfer. However, like evaporation, convection alone doesn't fully explain the complexity of the Mpemba effect. There are many variables at play, and isolating the impact of convection is challenging. Researchers have proposed various theories, but a definitive explanation remains elusive. The shape and material of the container, the surrounding environment, and even the initial distribution of heat within the water can all impact the behavior of convection currents. For instance, a wide, shallow container might promote more vigorous convection compared to a narrow, deep one. Similarly, the thermal conductivity of the container material can influence how heat is transferred to and from the water. These factors add layers of complexity to the study of convection and its role in the Mpemba effect. Scientists continue to conduct experiments to better understand these dynamics. By using advanced techniques and technologies, they aim to unravel the mysteries of convection and its implications for the Mpemba effect. This ongoing research not only deepens our knowledge of fluid dynamics but also has practical applications in various fields, from engineering to environmental science. Visual representations of convection currents in different scenarios can help illustrate these concepts. Whether it's the boiling of water in a pot, the circulation of air in the atmosphere, or the movement of magma beneath the Earth's crust, convection is a powerful and ubiquitous force. By studying these patterns, we can gain a better understanding of the natural world and the underlying principles that govern it. In conclusion, while convection currents offer a fascinating glimpse into the behavior of fluids, they are just one piece of the puzzle when it comes to understanding the Mpemba effect. The interplay of various factors makes this phenomenon a rich area for scientific exploration and discovery. To truly understand the Mpemba effect, we must delve into the microscopic world of water molecules. Water molecules are polar, meaning they have a slightly positive charge on one end and a slightly negative charge on the other. This polarity leads to hydrogen bonds, weak but significant attractions between neighboring water molecules. These hydrogen bonds influence how water molecules arrange themselves, particularly at different temperatures. Some scientists believe that the arrangement of water molecules in hot water might be more conducive to faster cooling and freezing. One theory suggests that hot water might have a higher concentration of pre-ordered clusters of molecules, resembling the structure of ice. These pre-existing ice-like structures might act as seeds for ice crystal formation, accelerating the freezing process. However, this hypothesis, like others, requires further investigation and experimental validation. Thanks for tuning in today. Don't forget to like, comment, and subscribe to go on our next fun fact-finding adventure. See you soon!